Good morning. So today's lecture, we will continue on ideal circuit elements. The last lecture, we already started with this section. So sources or the circuit elements can be either sources or elements that consuming power, which is, we call it passive elements. Sources, again, something that's used to generate power like current source, voltage source. Current source means provides constant currents. Voltage source means provide constant voltage. Then we have passive elements. So the word passive means these elements that cannot produce power, or in other words, only consuming power. Then these elements are called passive. So passive elements can be resistor, inductor, capacitor. So I think you are familiar of these elements from physics, resistor, inductor, capacitor, but here we will focus more on the practical thing. And I'm not sure about current source, if you are familiar with this from physics too, but anyway, so current source provides constant currents. So as we know, the resistance in ohms, inductance in henries, capacitance in farad, then the inductance is actually storing the energy as magnetic field, while capacitance storing the energy as electrical field. And most likely magnetic field related to the currents, while electric field related to the voltage. So in other words, I will say that inductance can store some of electrical current inside it, while capacitance can store some voltages on it. And most likely these elements are basically storage as charging, discharging. So hold, release, hold, release, hold, release, something like that. So inductor is hold, release for the current, while capacitance hold, release for the voltage. Okay, now the electrical quantities that we know from chapter 1 are voltages, currents, and power, right? And we discussed the power as absorbing power, supplying power. But the power is actually comes from the voltage and the current. So the basic two electrical quantities are the voltages and the currents. Now my target is what's the relationship between voltage and the currents using these passive elements? That's my question. So that's what we are going to discuss. So the voltage or the ratio or the relationship between the voltage and the current using inductor, resistor, and capacitor. Let's start up with the resistor. What's the relationship between the voltage and the current? So as we know, the voltage and the current are directly proportional to each other. Therefore, V, or the voltage, will be the proportional constant because it's directly proportional time, which is we call it R times I. And R we call it a resistor. And this is well known by Ohm's law, which is a linear relationship between the voltage and the currents. V equal R times I, or I times R, whatever. Therefore, if we need to calculate I, it will be V over R. So Ohm's law is well known for everyone, and basically it's a linear relationship between the voltage and the currents, such that R is the slope, or is the proportional constant, or the physical meaning is the resistance. This is, let's assume we have this system, and this is how the voltage and the currents associated with the resistors. So there is something important that we need to look for. Ohm's law is V equal I times R, which is everything is fine, everything is all right. Now my concern is related to the sign. Is it going to be I times R or negative I times R? So when should I put the negative sign? Why and how? So is there a rule how to set the negative sign? Yes. So that's the difference what we will have here or from physics. So most likely, recall what we used to assign for the power. We used to assign or look at the voltage polarity and current directions to determine if this element absorbing or supplying. Then the same scenario here. Okay, how? You need to make sure for every resistance there should be a voltage and currents. So you need to know the voltage polarity and the current direction. So I would say for every system we have 4 scenarios. I'm going to write them here. So we have scenario A, where here is the resistance. This is the polarity of the voltage of the resistance, and this is the current direction. Scenario B, it's the same resistor. Nothing changed with it. But I'm going to flip the sign of the voltage. How about scenario C? Also the same thing, but I'm going to reverse the current direction. Then scenario D, the same thing, but flip back the voltage polarity, while the current direction will be like this. Now for all of these 4 scenarios, A, B, C, D, they are all have same resistor. Then there is a voltage polarity, or they are all, we can say, like the same amount of voltage, the same amount of currents. But our concern is the voltage, or the sign actually, for Ohm's law. So I would say, if we need to apply Ohm's law, here V equal I times R, or R times I, whatever, V equal I times R, V equal I times R, V equal I times R. So it's the same as magnitude. They are all the same value. Now the thing that matters with us is it going to be positive or negative? How can we judge? Look at the current direction and voltage polarity. So if currents enters the positive polarity of voltage, then it will be positive. Ohm's law, I would say, like. Ohm's law positive. While the opposite, if the current enters the negative, then Ohm's law will be negative. That's number 1. Number 2, I'm going to write it down. If I enters negative polarity of voltage, then Ohm's law will be negative. So that's the simple rule. How can we apply it here? Look at scenario A. Look at the current direction and voltage polarity. Now, is the currents in scenario A entering the positive or the negative? The positive. So Ohm's law will be positive. That's it. Scenario B, the currents enters the negative. So what do you think Ohm's law will be? Negative. Enters the negative, negative. Enters the positive, positive. That's it. C, the current enters the positive, so Ohm's law, positive. Then scenario D, the last one, the current enters the negative, so negative. So that's it. That's all of the 4 possibilities. Okay, is this clear? So now, when we apply Ohm's law, we all know Ohm's law, V equal I times R. What matters with us is to determine the sign. Is it going to be positive or negative? And this, again, can be known by looking at the current direction and voltage polarity. So far, we will assume everything, or all of the voltage polarities, all of the current directions are given. That's what we'll assume now. Later, I think next week or the week after next week, I will give you some procedure in how to assign a voltage polarities and current directions. But not now. Now, let's assume that all of the current directions, all of the voltage polarities are given. Okay? All good? Now, how about the relationship between the voltage and the currents using the other passive elements, which is the resistors and inductors? Let's start with the inductor. The inductor, which is a storage element that's storing magnetic field. And magnetic field is related to the current, so I would say it is storing currents. Keep in mind, it's not a battery that's storing currents. It is just store small amounts and store and release. So it's not like we cannot say I can store my energy inside inductors. It's not like that. Okay? But however, we need to keep in mind that some practical things related to the inductor, for example, the transformer that transfer the voltage from one side to the other side, this is storing sometimes electrical currents. So when you disconnect the power, you are still not safe to touch the transformer. You cannot, or for example, let's assume some power utility company want to do a maintenance on a certain transformer. So when they disconnect the power, it's still unsafe to start their maintenance. Why? Even though there is no power source, because there is some residual currents or storing current inside this transformer, because this transformer equivalent circuit is based on inductance. So there are some inductance or some energy stored in this. So what they need to do, basically they will do earthing. So they will make the energy or that's inside the transformer to be discharged to the ground. So that's something we call earthing. So first, disconnect the power, isolating the components from the utility power, then earthing, so we can make sure we have a safe testing environment. One of the incidents, that's when I was working with a power company, which is the maintenance engineer forgot actually to do the earthing. So you disconnect the power, isolate everything, then say to the technicians, now you are good to go, let's start the maintenance. Then when they start the maintenance, they get shocked with this. It is, with the very big transformer, this might be, sometimes can kill some people, but fortunately they didn't die. They went to the hospital for a few days, then everything was all right after that. They opened an investigation. What's wrong? Why there's something happened there? Then they realized the maintenance engineer forgot to do the earthing. So sometimes knowing all of these concepts is very important, very crucial, because you can save some lives because of this. Okay? Then again, these components can storing some currents. So even though when you disconnect the power, it will still have some energy that need to be released. And it can be released by either connecting this to any load or released by connecting this to the ground by something called earthing. Okay, the relationship V equal L di by dt, so the time derivative of the currents. So it's changing with time. Then if we need to calculate the currents, just do the integral. So do the separation principle, make dt to this side, di to this side, and do the integral. Then it will be like these two forms. Basically, you can call like V equal L di by dt, and that's it. That's what you need to know. Then if you need to calculate the current, you can do the integration. Just do the integration, and I assume everyone knows how to do it. Okay, now one thing that we need to think about, which is there is a topic that we will discuss later, it's called DC. DC means constant currents. So if I is constant, what will happen? V equal L d by dt of constant. And this will yield to be the time derivative of a constant, and as we know, this was 0. So the voltage will be 0. Okay. If the voltage is 0, this means the voltage of point A equals to the voltage of point B. And in other words, this means A and B are connected to each other. And I would say this is called short circuit. Or as a shortcut, SC. So I would say in DC, the inductor will behave as short circuits. So you can remove the inductor and replace it by short circuit. So as we did here. Now it is short circuit. Replace it by a wire. Erase it and replace it by a wire. This happens if and only if you are in DC, or in other words, the current is constant. Okay? Now, how about the other thing, which is the capacitor? So the capacitor is also storage elements, but it's the opposite of the inductor. Actually, the inductor and the capacitor are the opposite of each other. Inductor, storing currents or storing magnetic field. Capacitor, storing, what's the opposite of magnetic field? Electrical field. What's the opposite of the currents? Voltage. So it's the opposite of everything. So I would say the capacitor is storing electrical field, or in other words, storing voltage. So I can say the duality, which is the inductor, is the opposite of the capacitor. So here, this is related to the currents. This is related to the voltage. Then this is related to magnetic field. While capacitor is related to electrical field. In the inductor, we used to say V equal L di by dt. Now in the capacitor, we will do the opposites. Replace V by I. Replace L by C. Replace I by V. So we will end up having I, and let me write them in lowercase. I equal C dV by dt. And that's how we got it, the relationship. So if you know one, then you can find the other. Yes?
Is there a difference between lowercase and capital I?
Yeah, so they are all must be lowercase actually. Yeah. So as in general, if we are working in AC, or like which is something that's changing with time, it will be lowercase. If we are working in DC, then it will be uppercase. So I think everything. So that's why when I write here I constant, since it's constant, it can be uppercase. But anyway, so far, I mean, now it's not. That's fine if you are mistaken with this. But later we will give you some rules. Then we need to follow it. That's if it's constant, then must be uppercase. Okay, so again, the duality for the currents and the voltage, so or for the inductor and the capacitor as well. You just know one rule, which is V equal L di by dt, while you can derive the other from it. Replace I by V, V by I, L by C. So we will end up having I equal C dV by dt. Then if we need to calculate the voltage, you can do the integral. Okay? Does this make sense? Now the other thing, which is how can I make sure of these relationships are positive or negative sign? Is it going to be positive sign or negative? So sometimes, like I say, I equal negative C dV by dt, or I can say I equal positive C dV by t. This is depending, again, the same thing that when we apply to the resistor, we can apply it here. So if currents, if I enters, let me write in lowercase, enters negative of V, or here if I enters positive of V. If the current enters the positive polarity, then that's positive. If the current enters the negative polarity, that's negative. The same thing for the inductor formula, the same thing for the capacitor formula, and the resistor formula. Okay? Is this clear? Any question? Now, how about if I assume voltage is constant? If V is constant. If the voltage is constant, then I will be C d by dt of the constant. The time derivative of the constant is 0. Therefore, the current will be 0. So in DC, the capacitor current will be 0. So what does 0 current mean? In order to have a 0 current, we need to either have disconnect the source, which is we cannot disconnect the source because it's already been connected, or the other thing, make it open circuit, right? Which is make it open path or open circuit. So the only way to make it 0, we will replace this circuit or this inductor by this. So here the voltage still exists, but the current equals to 0. This is called open circuits, or as shortcut OC. Okay? Then this can happen if and only if in DC. In DC. DC direct current means constant voltage, constant currents. DC, again, we will discuss it later, but here it's worth to mention that if the voltage is constant, then it will be open circuits. Or if in DC, the capacitor will be open circuits and the inductor will be short circuits. Just replace it. Then you don't need to apply the formula I equals C dV by dt or V equal L di by dt because it's DC. And again, DC means constant voltage, constant current. Any question on capacitor, inductor, resistor? Okay. Let's see an example here. Consider the box of each previous examples, which is we need to apply the voltage and current relationship. So we have the voltage as 10 e power negative 3. The initial condition I of 0 equals 0. Then we need to determine the currents. Okay, so for the first for the first example, we need to calculate the currents. As we know in Ohm's law, V equal I times R, or let me write them in lower cases. V equal I times R. Then we need to calculate the current, so I will be V over R. So V is given as 10 e power negative 3t, while R is given as 2, so it will be 5 e power negative 3t. And the unit, of course, is amperes. Okay? How about the inductance? We know V equal L di by dt. My target is to calculate the currents. How to calculate the current? We can do the integral formula, which is I of t will be 1 over L, the time integral from 0 to t, V of t dt plus I of 0. Now it's time to substitute the formulas. So it's going to be 1 over L, L given as 2, 1 over 2, the integral from 0 to t. V of t is 10 e power negative 3t dt. I of 0 is given as 0, so plus 0. Therefore, it will be as 1/2 times 10. Then the integral of the exponential is 1 over the constant times the exponential itself. And the time period between 0 to t. Okay? Then it's going to be as 10 over 2, 5, negative 5 over 3. Now substitute e power negative 3t minus e power 0 because negative 3 times 0 e to the power negative 0, which is 1. Then the answer will be negative 5 over 3 e power negative 3t minus 1. Sometimes we don't want the negative sign, so we can put it here and here. So what will be? It will be written as 5 over 3, 1 minus e power negative 3t, and the unit is amperes. Okay? It's just like math. Now the next question, or the next part, we need to calculate the current for the capacitor. We know the formula I equals C dV by dt. C is given as 2, the time derivative of v of t, which is 10 e power negative 3t. Then 2 times the constant 10. The derivative of the exponential, we will put negative 3 here. Then times the exponential itself. So 2 times 10, 20, times 3, 60. There is a negative 60. E power negative 3t amperes. This is I of t. Okay? Again, this is just a math. Just do the math and that's it. Any question? Okay, may give you some time to write, then we will go next to the open circuit and short circuit. Okay. Now, let's go more in open circuit and short circuit. So open circuit, as a shortcut, we will call it OC. And basically, we will say that open circuit where the current equals 0, while the voltage is non-zero. The voltage cannot be 0. Only the current is 0. How can we achieve this? The voltage is 0. Voltage is not 0, while the current is 0. This can be achieved by making this system like open circuit plus minus. Here is voltage A, voltage B. Here is the current. Of course, the current is 0, while the voltage is non-zero. Okay? So in this situation, the currents cannot be 0. I'm sorry, the current is 0, but the voltage, of course, is not 0. What's an example of the open circuits is the wall outlets. The wall outlets, there is voltage. You can prove this, bring a digital multimeter, put it inside the socket. Then you will see that we have a reading. So there is a voltage. But there is no current because it's open circuit. There is no closed path for the current to flow. Therefore, it is 0. Okay? Now, another thing, as we know, Ohm's law, V equal I times R. So therefore, I will be V over R. If we assumed R is equal to infinity, then of course, so this will yield to 0. So if we assumed R infinity, again, this is also open circuits. So sometimes there is a resistive model for the open circuit by assuming the resistor equal to infinity. That's another way of presenting. But the way that I like is just to make it open. It's open circuit, make it open. Now, how about short circuit? As a shortcut, we will call it SC. So open circuit and short circuit are opposite of each other. So here, where is the voltage is 0, while the current is not 0, is non-zero. So this is the opposite of short circuit. How can we achieve this? We can achieve this by having this system. Here is I, here is plus minus voltage. Since A and B are the same point, there is no voltage difference. Therefore, V equals 0, but I is not necessarily to be 0. Okay, so this is called short circuit. While, and you can see also under this short circuit, there is no elements, so we just connect these 2 points. And while if we would say like the resistor model, if you need to apply Ohm's law, V equal I times R, if we assume R equals 0, so V will be 0 times R, I times 0, then this will yield to 0 voltage. So the resistive model of the short circuit is also the voltage equal to 0. Okay? Clear? Now I would just want to also discuss something which is related to the wall outlets. So the wall outlet has 3 sockets. So one of them for live, the one for the neutral, the third one for the ground. Most likely the third one for the ground is used for protection. Sometimes if there's short circuit happening, there will be current flowing through, or something wrong with your device, there will be current flowing through the ground. Then we have a detector that detects if there's current going through the ground, then we will turn off the power, which means there is a current leakage, leakage going on. Then the power will be off to protect you from fire, to protect from any other devices, any problems. So most likely, that's why we'll see ground in many applications, especially in large applications like refrigerator, some other stuff, some other devices that we need to use the ground. However, in order to make this system functioning well, the ground is not necessarily. The ground, again, for protection. In other words, you can use live and neutral and that's it, then the system can work. Look at your cell phone charger. Cell phone charger has only 2. And it's actually low power, low currents, so it will not cause any fires or anything because it has low power. So there is no need for protection to have a ground. And also some other devices, there is no ground with this. That's fine. So in order to have a complete thing, which is you need to have live and neutral. So for example, live is the positive part, neutral is the negative. Okay, that's something similar to this. Not exactly, which is because we will talk about this later. But now, I would say the wall plug here, this plug, is by nature, it's open circuit. If you are not connecting anything, it's open circuit, right? When you connect a device, it will be short circuit, right? And the equivalent circuit of it, we will say this is a voltage source. So this is live, this is neutral. Okay? So it's not connected to anything. Now, my question is, if you bring a wire between live and neutral, connect a wire, I'll put your both hands here. Put your both hands, or connect a wire here. What will happen? Of course it's dangerous, right? If you put a wire, sometimes it might cause fires. This might cause some problems, right? If you put your hand like this. So what's the problem? Why there will be a problem or causes fires? If you connect live and neutral together, you are making this the equivalent circuit like this, right? So let's look at the currents. This is point A, this is point B. Okay? So according to Ohm's law, I equal V over R, right? Here the voltage, let's assume 120 volts. The resistor, there is no resistance, right? So 120 over 0. And any number over 0 is what? Infinity. So infinity, in real life or in engineering, we have defined the infinity, or we can define the infinity as a very large number. It's not like math, which is the largest number that we ever know. No, here infinity means very big number. Very large number. Very large currents. So again, here's something, also you'll see this later in this course, we will define the infinity by a specific number. We can define it as, but again, very large quantity. So when you connect this will cause a short circuit, which means a very large current will flow, sometimes causes fires. But actually, in real life, practical life, if the protection system is well designed, then it shouldn't cause fires. So what will happen? The circuit breaker will trip. This will protect you, protect your life, protect from fire. So we should have a circuit panel that protects, that will trip, and this circuit breaker will trip, then there will be no power, then there will not be any other damages. So that's what's supposed to be. But sometimes the circuit breaker might have some failures, or the settings might have some problems. So again, it's still dangerous to do that. But I mean, if this happens in the past and there is nothing, no harm done has been occurred because this is because of the circuit breaker. Basically, the circuit breaker will detect if there is a high current. If there is any high currents going on, this means there is something wrong, then the circuit breaker will trip. The circuit breaker is detecting high currents and avoid fires, damages, save lives. Okay? Any question? Then my last question before starting the quiz. Which one is worse? Short circuit or open circuits? Short circuit. Why? Because the currents, right? High currents. While open circuit, we see it everywhere. Any wall outlets. Open circuit, right? Okay, so let me end the lecture.